Hello, Professor Chakraborty.
Yes, yes, I'm here.
So may I
So,
share the screen?
yeah. Start.
Is it visible?
Yeah, it's coming now. Yeah. Can it be made full screen so that other people can also see it? Can it be?
This is the maximum.
Okay, okay, is it visible to everyone else? Just confirm. Even those who are using their mobile phones, I hope it is not too small for them.
Anisha?
Oh, it's visible.
Yeah. Okay.
Okay.
Okay, then please take over.
Okay, so let me start today. So yesterday I did basically compact groups like orthogonal groups, unitary groups like UN, SUN, things like that. So today we are going to discuss basically the Lorentz and Poincare groups, which are actually non-compact groups. Okay. Nevertheless, when they act on Hilbert spaces of quantum systems, they will act through unitary representations. So we'll come to that point later. But first of all, let me start defining the Lorentz group, or rather the double cover group, SL2C, the way I introduce it through the root of SU2 group itself. And let me see how it goes. Okay, so can you show the slide, first page? No. Next. Okay. So you recall that SU2 group we had already defined yesterday, and so far it has been used by many people now, so you must be quite familiar. And we also introduced the SU2 real algebra, which is basically obtained by taking the linear span of the Pauli matrices with real coefficients. So we write SU2 as a span of Pauli matrices sigmas with real coefficients. So it has three independent parameters. Now what we do now, we define the corresponding Lie algebra of SL2C as something very similar to SU2, except that the field of real numbers is being extended to the field of complex numbers. In the process, we are doubling the number of independent parameters from 3 to 6. D of SL2C will be 6. So in the process, what we are doing, any arbitrary element of SU2 could be parameterized as e to the power I by 2 theta dot sigma. Now instead of theta, we are allowed to write theta plus I phi dot sigma. So we have complexified SU2, so to say. So that will, since you see the I phi, the phi term, basically there is a prefactor I also. So this I will cancel. So it will become essentially phi dot sigma. So this is the reason that it will become basically non-compact. And any arbitrary group element that you will obtain will not have any unitary properties. All that we are left with is simply the determinant equal to 1 condition. And this is the SL2C algebra. So it is just a simple generalization of SU2 by complexification, so to say. We'll see that it is intimately related to the Lorentz group. So for that, let us consider a 4-vector P mu. It can be any 4-vector, need not be energy momentum 4-vector, for which it is generally associated. Any 4-vector which transforms as a 4 contravariant vector under Lorentz transformation in 1 plus 3 dimensional Minkowski space. Throughout my lectures, I will employ the signature which is mostly positive, that is minus plus plus plus. Okay, so please go to the next slide, please. Next slide, please. Okay. Now associated to this four vector, I cause means I associate this 2 by 2 matrix which I define to be sigma mu p mu to this four vector p mu, where this sigma mu is just is defined to be identity and sigma, three Pauli matrices, and that sigma 0 is just identity, the way I defined it. So if you expand, you are going to get this Hermitian matrix, but now it will no longer be traceful. It will be having finite trace as long as P naught is non-zero. Okay, so this is the way I associate this. This is called a bispinner, and this bispinner associated with any P mu matrix, four vector P mu. Okay, now you observe that if you have this M, which is an SL2C matrix, and if you subject this bispinner a transformation of this form, sigma dot P going to M sigma dot P M dagger, the harmonicity property will be retained. Determinant also will be preserved. But the determinant you see, it is simply P dot square minus P vector square. Precisely the way we introduce the so-called quote-unquote norm of a four vector in Minkowski space. I should say quote-unquote I am saying because you should be careful, it is not positive definite, because depending upon P naught exceeds P vector square, P naught exceeds the magnitude of P vector, it will be time-like or space-like. Or means if it is more, then it is time-like, otherwise it will be space-like, or if it is equal, then it is light-like. Anyway, I am not talking about all these things now, but the point is that it preserves the Lorentz norm, so to say, or Minkowski norm, you can say, is preserved. So you can identify this transformation to be a Lorentz transformation. There must, just like in SU2 case, you could see the norm of the three vector is preserved under SU2 transformation in a similar manner. So here also we find the Lorentz norm is preserved under this SL2C matrix. But again, like SU2, if N and M does this job, induces this transformation, which I call is SO1, 3. 1 is because there is signature difference. P naught has a square has a positive sign in front, and P vector, there are three such terms having a 3 minus sign. So it will be SO1, 3. So it is not completely orthogonal group, it's called pseudo-orthogonal group. So if M induces this SO1, 3 transformation, so does minus M, and in the process we find that there is a Z2 ambiguity, so we need to quotient that out, just like SU2 quotiented with Z2 give SO3. Here also we are going to get SO1, 3. So here SO1, 3 I should be more specific, because in the O3 case I had determinant +1 -1 sector. So here also, if you remove this S part, you are going to get simply O1, 3, which will have again determinant plus and -1. But again, you can have disconnected part with the positive determinant also, which will involve simultaneous spatial inversion and temporal time reversal transformation. So you take T going to -T, R3 vector going to -R3 vector. That will also involve a determinant +1 condition. So again, that will be also not connected to identity. So what we are doing, we are going to confine our attention to only those part of O1, 3, which is connected to identity and which is called proper orthochronous Lorentz group. It is a subgroup of the complete O1, 3 group. Screen disappeared. I think again there's problem from, so Annesha, can you just share the screen?
Annesha, can you please share the screen? Okay, I have joined, I guess. Okay.
Yeah,
Yeah,
you are.
Amnesha also has left the meeting access.
Amrita is not required, are they? Should I change the slide?
Uh, oh, yeah, it is coming. Okay. Okay. So please go to the next slide. Okay, so now just like in SU2 case, we could find the generators by considering an elements of the SU2 group very close to the identity and read out basically the generators. Exactly the similar task you can undertake and find out the 6 generators now, because the number of generators is now doubled to 6 as I already told, and you can identify 3 old generators which are basically like the SU2 generators, which are given in terms of J's. They satisfy usual SU2 Lie algebra, Ji, Jj, I epsilon, I, j, k, j, k. Whereas you will get 3 more additional generators which are Ki, Kj, but Ki, Kj will not, there is a mistake here. Ki, Kj will be minus I epsilon, Jk, Jk. It will not close to a Lie algebra. Okay, there is a mistake. So the boosts do not form a sub-algebra, but all that you can say is that GIS is the generator rotation, the boost generator, the transform is a vector under 3-dimensional rotation. That the Gi Kj is I epsilon ijk kk. It shows that it indeed transform as is true. And Gi Jj is of course the sub-algebra, SU2 sub-algebra of SL2C. So SL2C you see is a bigger group than SU2 because the unitary condition has been relaxed now. Okay. So the Ks are the boost generators and the J's are the usual rotation generators. So again, the fundamental representation, as far as fundamental representations are concerned, you can identify the J's to be original, the sigma by 2, and K will carry another factor of I in front of. So you can have K equal to either plus or minus I sigma by 2. And this is the fact that K is non-Hermitian is responsible for the non-compactness property of the group. So nevertheless, it is possible to have built up higher order or general irreducible representations, I simply say reps, by constructing this kind of Hermitian generator A plus minus as half J plus minus IK. They individually satisfy the plus sector will satisfy SU2 Lie algebra, likewise the minus sector also will satisfy SU2 Lie algebra, but in between them they will have vanishing commutation relation. So it shows that these algebra correspond to SU2 cross SU2 algebra, and this facilitates the the process of representation by using a pair of SU2 indices J and J prime. So you can import all these machineries of SU2 representations. Only thing is that here you need a pair of such indices J and J prime to represent an arbitrary Lorentz group. Okay. So please go to the next slide. So let me consider the special cases. So I have designated J comma J prime is some representation. J is the SU1, SU2 index, and J prime correspond to the index. So let me consider J0. So in this case, A minus is completely 0 and 0J where A plus is completely 0. You can see that in this case, J's and K's will be related like this. J will be IK and J, another case will be J equal to minus IK in the Jth representation. So we can introduce 2 types of spinors. In the first case, in the fundamental representation case where J equal to half, let me consider J half is equal to IK half equal to sigma by 2. So let me consider this an element of C2 which transforms under just like in SU2 case, but now they are subjected to SL2C transformation. So it will transform like this, e to the power I theta dot J half plus phi dot K half acting on xi. So I can just substitute J half and K half as above, I'll get this kind of structure. I call this matrix to be M, which acts on xi to generate another element of C2. Likewise, for 0 half, the type 2 0 half case, where J half will be minus A half, it will be minus sigma by 2. In this case, the corresponding spinor I denote it by eta, which transforms by, say, some SL2C matrix, which I call it M. The first one is M, which corresponds, you can see that from the structure, the sign of phi has got flipped. So one is denoted by M, another case the matrix is denoted by N. Okay, next, go to the next slide. Please. Yeah. So in either case, again, you can verify the determinant of M or N, and slash means it's or. Determinant of M or N is, you can just write e to the power log of determinant of this thing. It's a tautological statement. Then log of determinant is trace log these things. Again, N is the exponent e to the power something. So this vector will come, the exponent will come down, and you are left with the task of taking trace of this object, e to the power I, trace of half sigma dot theta minus plus I phi. But sigmas are traceless, as I have told you earlier, so e to the power 0, that will be 1. It shows that it's an also 2 by 2 matrix having determinant 1. So both M and N are SL2C elements. Why I have used the two matrices M and N, why it was not sufficient to work with M and N, it is clear from the fact that M and N furnishes inequivalent representation of the Lorentz SL2C. Because there are no similarity transformation which can correct these things. Then, in other words, there is no S by which you can write N is equal to S M S inverse. Rather, you have to, you can, all that you can do is you can write N equal to S M star, means zeta M star zeta inverse, or zeta equal to minus I sigma 2. This can be easily verified. All that you have to do is a simple identity that is satisfied by Pauli matrices. Sigma 2, sigma vector star, sigma 2 is equal to minus sigma. That you can easily verify just component wise. Just star will be effective only for the sigma 2 part, because which has imaginary components. Otherwise, for sigma 1 and sigma 3, it will not be affected, and it will follow by simple invoking the Clifford algebra. The sigma 1, sigma 2 product is basically I sigma 3, something like this. So you can, from there, you can easily verify these things. Another thing is that, which is going to be useful for us in later part of the day, if you have xi, which transforms as far as under SU2 in the half zero representation, you can easily show that if you take xi star and multiply by sigma 2 and transform it in the following manner, you will see that sigma 2 xi star transforms like N. So, in other words, I write I sigma 2 xi star transforms like eta. So xi and eta, they were transforming as xi was transforming as a half zero representation, but you can show by simple algebra that I sigma to xi star will transform like eta. So you have to take a complex conjugation, okay, to generate this thing. So I'll use this fact later. And similarly, other thing also, which I have not written down, is I sigma to eta star will transform like xi. Like that means from half zero half representation, you can come to half zero representation, vice versa. Okay. Okay, please go to the next slide. So now let me relabel this matrices M and N by lambda L and lambda R. And xi as psi L and psi R. The reason behind is that, as I mentioned earlier, these two matrices differ just in the sign of phi, and phi is actually related to the boost parameter. So whether you are boosting in the positive, say, x direction or negative x direction, this is the only difference it is making. nowhere else. Okay, so in one case I want to associate with some left-handedness, another case I want to associate with the right-handedness. So I label xi as Shayal and eta as Shayar, and they are basically what are known as chiral spinner, chiral SL2C spinner. Earlier, you see, yesterday I spoke about SU2 spinners. Now it is more general SL2C spinners because they transform under SL2C transformation. Now, out of this, from this Shayal and Shayar, there are two component spinner. I can construct a four component spinner in the following way. Capital Psi is equal to Shayal Shayar, which transform is half zero, direct sub zero half representation of the SL2C. The component, the top component transform as half zero representation, and the lower component transform as zero half representation. And this four component spinner is known as Dirac spinner. You may be surprised that why I am going from some irreducible representation I had to some reducible representation now. Because you can easily see that under Lorentz transformation, Shayal and Shayar they transform independently. The former transform, the top one transforms by d lambda, and the bottom one transforms by d bar lambda, where d bar lambda is just the flipping of sign, is obtained by flipping of sign of phi, and related to d lambda by the complex conjugation and taking similarity transformation zeta d star lambda, where lambda is typically Lorentz matrix that Professor Dashgupta has already introduced before. Okay, so please go to. So at this stage, it provides a reducible representation. Nevertheless, I can enlarge the group by invoking parity, because under parity, Shayal and Shayar will flip their sign. So I can write under parity, Shai goes to Shai P, which is Shayar in the top now, and Shayal, and it's related to Shayal and Shayar by this matrix. So here I introduce a new matrix which I call gamma naught, with the time component, the gamma matrix gamma mu that I introduce in the next couple of slides. I define it like this. So I can introduce like this I gamma naught Shai. But gamma naught is this matrix. Comments on the following, as I already mentioned, Lorentz group is non-compact. The boost part is basically responsible for it because it has this structure. So unitary representation of the Lorentz group is necessarily infinite dimensional. You cannot have finite dimensional unitary representation of non-compact group like Lorentz group, particularly the boost part. Okay. Okay, next slide, please. Okay. No, it has come back next one. Next to next.
Should I go to next?
Yeah, next one. Okay, so now you can see from this simple group theoretical consideration, we can go towards the derivation of Dirac equation in some sense. Because suppose we are considering a massive particle which we expect to be describable by this kind of spinners, and since massive particle, we can think that the massive particle is at rest, where the psi 0 is the form of the spinner value wave function and the rest frame. Now you give a boost to it. I by 2, then the I should not be there. There should not be I. The boost should be just half sigma dot phi. Because it is non-compact. I think it is a mistake has percolated. I did not notice it. Anyway, so I should not be there. So Shayar P will be e to the power half sigma dot phi, psi 0, and Shayar P will be minus half sigma dot phi, psi 0. Now you can eliminate psi 0, or Shayar you can write it as, just remove the I from all these, from the exponent in all these cases. Shayar P will be related to Shayar P like this, and or Shayar P will be related to Shayar P, just flipping the sign. And these two relations now can be clubbed together again in the by making use of the Dirac spinner by first employing some kinematical relation which you know from your BSc days, that if you consider a Lorentz boost, which you can write to be some of the form of Lorentz matrix, if you consider boost along say x-axis, you have this formula x minus vt, means I'm working c equal to 1 units, okay, x minus vt by 1 root over 1 minus v square and things like that, and likewise for t and things like that. So you can cast it in the form of this cos hyperbolic phi sin hyperbolic phi sin hyperbolic cos hyperbolic phi. You can see that is a symmetric matrix of determinant 1, and this phi is related to the velocity v, okay, which is always less than 1 in our unit c equal to 1. So the boost also looks almost like a rotation matrix usually, except that the hyperbolic function is a symmetric function. So anyway, so next slide please. So there are a couple of kinematic relations which you can employ. Next slide please. So this kinematic relations, gamma is, you can write down as cos phi, cos hyperbolic phi, and E equal to gamma m, that you know already. Using this, these above two equations, above pair of equations can be recasted in this form. Okay, I'll come to this pair of equations later also. So this pair of equations now we combine with the Dirac-Spinozha in a compact form like this. It is a matter of simple algebra where psi L and psi R are the two upper and lower components of the four component Dirac spinors. You can write it more compactly in this form. And this is the famous Dirac equation in momentum space, where gamma mu has this representation. Sigma mu I have already introduced. In addition, I have sigma bar mu. There should be a comma between sigma mu and sigma bar mu, where the sign of I2 flips. Sigma bar mu will be minus I2 comma sigma. These are the famous gamma matrices in the chiral representation. Dirac's famous gamma matrix in chiral representation, and they satisfy, which you can check easily, the famous Clifford algebra, gamma mu anti-commutator. It means the gamma mu plus gamma nu is equal to twice eta mu nu times some identity matrix in four dimension. And as I told you, eta mu are taken mostly positive, so the diagonal form will be minus 1, 1, 1. So this is the way I can, from good theoretical consideration, I can get hold to the basic structure of the Dirac equation. So you can cast it in the coordinate x space also, where it will take. Please go to the next slide. Next slide, please. Yeah. So, no, next. No, slide before that. Slide before that. Okay. Okay. So now you can see that if you apply I gamma mu p nu on both sides of the Dirac equation, you will get the p square plus m square acting on psi p is 0. The coordinate space, it will take box minus m square acting on psi is equal to 0. Box here, of course, the definition I am working with is something which will give you minus del t square plus the Laplacian. Okay. So anyway, so it shows that each of the four components individually satisfy the Klein-Gordon equation, which it must, as it corresponds to basic Einstein's energy momentum relation. Okay, where we have of course taken C to be 1. Okay. Please go to the next slide. Okay. So now let me see. So far we have dealt with the massive case. Now and also introduce the Dirac spinor. Now let me introduce what are called the Weyl spinors. So Weyl spinors correspond to what is a massless case. So let me go back a couple of slides before the equation which occurs in the blue color. 2 slides back, please. 2 slides back. 2 slides back. Another slide. No, back. Yeah. So you see now, I'm so far I've been no. Stick to that. This pair of blue equations. Uh, previous page, previous slide. No, previous. You're going previous one slide back. One slide back, please. No. Go forward.
Back means you want to go forward, right? So, yeah.
It's not audible. Means below. One slide. Here. Stick here. Yeah. Stick here. So now, so far I have dealt with the massive case. Now, to discuss massless case, I just simply put m equal to 0, and in the left hand side, so both the equations will have vanishing left hand side, and we will be left with E plus sigma dot p acting on psi l equal to 0, and E minus sigma dot p acting on psi l is equal to 0. So psi l and psi r, that get decoupled in the sense. Though individually they follow individual, they are independent equations. Okay, and these are psi l and psi r are called the Weyl spinors. Some massless particles, if there are any, which are spin half, because in this scenario, if you quantize, you can see the particles which emerge out of quantization will necessarily have spin half quantum number. So these particles, massless fermions, will necessarily be described by this kind of Weyl fermions. So please go to this slide of Weyl fermion. Just go forward to a couple of slides. Massless case. Massless case. Weyl spinors. Right. No. Weyl spinor. Wait, go back. Stick here. Weyl spinor. So massless case, as I've shown, we have a pair of decoupled Weyl equations. P0 minus sigma dot p acting on psi r p is equal to 0, and P0 plus sigma dot p acting on psi l p is equal to 0. And the psi l are called left-handed Weyl spinors, and psi r's are the right-handed Weyl spinors. In a more compact form, of course, you can write it like this: sigma mu p mu acting on psi r is equal to 0, or sigma bar mu p mu acting on psi l p is equal to 0. Since they are massless particles, the P0, the energy, will be basically the magnitude of the 3 momentum. So an alternative form of the pair of equation is sigma dot p acting on psi l will be minus psi l, and sigma dot p acting on psi r will be psi r. So, hello.
I want to ask a question that here P not equal to mod of P. Why P not equal to plus minus mod of P?
No, I'm considering positive energy particles.
What happened the negative energy part?
No, negative energy.
Because the relativistic case of both energy are allowed.
Kinematically allowed, but physically not possible. It will come in the quantization. When you quantize, then you will have to get rid of the negative energy part somehow. No, you do it. It is a matter of physics. When you do quantum field theory, then you get rid of the negative energy part by.
But at this stage, you are not doing. Are you doing quantum?
No. I am not interested at this stage to address this question.
Then how you can ignore?
Why can't I ignore? I am restricting myself. I'm restricting myself to positive energy case. In negative energy case, these questions will come only when we do relativistic quantum field theory, and upon second quantization, I can get rid of something like normal ordering and things like that. I have to get rid of the negative energy part. So this is a physics question. You will do it if you do quantum field theory. Okay, it is beyond the jurisdiction of this discussion. Okay, so what?
Okay.
Yes.
I mean, but the spectrum of the momentum, linear momentum is not bounded from below. It goes from minus infinity to plus infinity because the p0 is p0 acting on psi r equal to sigma dot p acting on psi r. Therefore, spectrum of the p0 is goes from minus infinity to plus infinity, na? According to the
You can have. In fact, that happens with the Klein-Gordon theory also. No, then you have negative energy problems. Then you get rid of it when only at the level of second quantization, while you carry out normal ordering and all that. Then you get rid of all these problems. The classical level, you can have admissible values of negative energy also. But at the quantum level, you have to do. That's why the normal ordering and field theory descriptions are coming in. But here I am not bothering about any such quantization and anything like
so
this.
at this stage you are discussing all classically, I think.
Exactly, classically.
Okay,
These questions are not relevant at all in this case, and I'm
that
also
means,
considering that P naught is positive.
Okay, that means P is no longer an operator on Hilbert space.
No. It is a simple classical thing. Means I'm doing simple classical mechanical consideration.
Okay.
Nowhere so now this thing P naught is not P. So alternative form of this above pair of equation is sigma dot P hat. P hat is a unit vector in the direction of momentum, is an operator which gives rise to minus eigenvalue acting on psi L and plus one eigenvalue acting on psi R. So if you recall that half sigma is the spin operator, so component of spin in the direction of momentum is minus half for psi L and plus half for psi R. That's why this terminology of left and right handed, and these are called helicities. The component of momentum, a component of angular momentum, particularly spin in this case, in the direction of momentum, is minus half or plus half respectively, and these are called helicity eigenvalues. Okay, I'll have more to say about these things from a more rigorous approach using Wigner's little group tomorrow. Okay, so go to the next slide, please. So I have introduced Dirac spinner, then Weyl spinner, and next come the Majorana spinner. As I have already told you that you can find that you multiply or take the complex conjugation of psi r and multiply by sigma 2. Complex conjugation of psi r and multiply by sigma 2. The object will transform in exactly the same manner as psi l. Likewise, sigma 2 psi l star will transform exactly like psi r. So that as far as transformation property under SL2 is concerned, they are basically same. That means psi l, if they transform like by lambda l, sigma 2 psi r star also will transform through lambda l, though psi r occurs there. Likewise for sigma 2 psi l star, it transform by lambda r rather than lambda l. Okay. So as far as transformation property is concerned, the Dirac spinner, we can build a four-component spinner psi m just from psi l by just replacing. So in the case of original Dirac spinner, we have psi l and psi r. We just replace psi r by minus sigma 2 psi l star. Minus sign, I'm coming to a point why I'm introducing a minus sign. But as far as transformation property is concerned, you see this transform as half zero direct sum 0/2 representation of the Dirac spinner. So this object, two-component spinner, which is built out of entirely psi l only, is called a Majorana spinor. And since it is built up of Chial only, it has only half the degrees of freedom of Dirac spinor, not the total degrees of freedom of the Dirac spinors. Okay. Now the minus sign comes from the fact that if you put the minus sign, you can show that it is invariant under charge conjugation symmetry. That means, in other words, it is self-charge conjugate. What is a charge conjugation symmetry? I don't know whether everybody knows about it. If you study Dirac equation and couple the Dirac particle to background electromagnetic field, then there will be some minimal subscription postulate where you can generate some interaction term. So you can ask the question, what will be the Dirac equation of a particle which carries opposite charge but with equal mass, which are called antiparticle? You can see that those equations can also be derived, and it involves some sort of some what is called anti-unitary transformation, which will come later in the talk today. And this is called charge conjugation symmetry. And under charge conjugation, Majorana spinors is self-charge conjugate. That means if you apply the charge conjugation operator on psi m, which will produce the psi m. I'm just giving you this information. I'm not discussing it here. I will not have enough time to discuss this. Okay. So can you go to the next slide, please? And also, just by the way, some comment that Majorana spinors is also, means so far as I know, no physical observation has been made where any particle, elementary particle, can be described by Majorana spinor. But there's some candidate. For example, neutrinos are supposed to be massive now, so they are no longer. It is no longer possible to describe them by Weyl spinor. So Majorana spinor is a possible candidate, but I don't know about the latest experimental status in this direction. Perhaps you can ask Sir Latham Boyle when he gives his talk, because he's an expert on standard model and latest experimental situation also he will be able to tell you. Okay. So now let me come to from the Lorentz group to Poincare group. Poincare group also Professor Dasgupta has spoken to you about it. It is an extension of the homogeneous Lorentz group, and Poincare group is also sometimes called as inhomogeneous Lorentz group. That's why inhomogeneous I, SO1, 3. I stands for inhomogeneous, SO1, 3 is the Lorentz group, inhomogeneous Lorentz group. Recall, in flat spacetime, the line element ds square is eta mu nu dx mu dx nu. To make a Lorentz transformation, inhomogeneous Lorentz transformation, means x mu going to x prime mu, which is lambda mu rho x rho plus a mu, then this line element will be invariant. In other words, you can show that eta mu nu lambda mu rho lambda nu sigma will be eta rho sigma itself. The eta will be invariant. Or more compactly, if you write using matrix notation, then you will get lambda transpose eta lambda equal to eta itself. So eta will be preserved. So this is called pseudo orthonormality condition, because when you consider orthogonal group, instead of eta you had identity. Then you had what is called orthogonal group. Now instead of identity you have eta, which is the form of -1 + 1 + 1 + 1. So almost like identity, except that the time component has split to sign. So it's called pseudo orthogonal group. But here too, as I mentioned earlier, determinant will be restricted to + and -1. This Poincare group will now be, again, this thing as Professor Dasgupta has already mentioned. I'm just mentioning it for completeness. And for brevity, I'm just skipping many of the details here. So you take some pair of elements which are, you can denote it by lambda comma a and compose it with lambda bar a. This will be the composition rule. He has also discussed about it. And this composition rule is a bit different from the direct product rule, because direct product case, you will get in the second slot, you will get just a plus a prime. So translation will behave just like your own translation group, with 0 is the identity operator, that's the additive identity, and for lambda it will be multiplicative identity. So it will be 1, 0, that will be the identity element of the Poincare group. 1 means the identity 4 by 4 identity matrix. Since it is something different, it's called semi-direct product, and lambda corresponds to homogeneous Lorentz transformation matrix, mu corresponds to 4 vector representing the translation. Please go to the next slide. Inverse element you can easily check by using the multiplication rule. This is really the inverse element. If you take the product, then you will get 1, 0 as the identity element of the Poincare group. Okay. Now, as far as Lie algebra is concerned, you can again take the 4-dimensional representation for the homogeneous Lorentz group, but for translation you have to extend it to some, add another 5th row and 5th column, and it is easy to do that. You put all the elements to be 0 everywhere except in the last column you put it 1, something like this, and you study the elements close to the identity, infinite small distance from the identity, identify the Lorentz generators or Poincare generators. You will find that they satisfy this kind of algebra, which I have written in covariant form. Okay, I'll derive this, show you how these relations are derived when I make them act on some quantum states, and they will all become unitary operators. Here they are not all unitary operators except rotation and the boost part, because J0I will correspond to your boost, and Jij they will correspond to the rotation generators. Rotation generators will be Hermitian even in this state. The boosts are not, and which will become Hermitian only when they act on quantum states of Hilbert space states. Okay. So you can see this is a Lorentz generator ISO3. So SO1, 3 has 6 generators, and the translation 4. So total there are 10 generators. So P mu's are the 4 such generators which mutually commute among themselves. 4 such generators. And J mu nu, they are of course antisymmetric. So for every plane you have such a generator. So there are 4 C2 number of these things. So there are 6 such generators. Total adds up to 10. Okay, please go on. Next slide, please. Next slide, please. Yeah. So now let me study how this Poincare group act on quantum states. Let me start with a very brief and fast review of the basic postulates of quantum mechanics, which I hope all of you know, just to recapitulate and to have the notation also settled for once and for all for the rest of my lecture. So you recall that physical states are represented by rays are in the Hilbert space. Because you remember, if you given a state psi, you can scale it, lambda times psi. It will represent the same physical state basically. And lambda can be arbitrary non-vanishing complex number. So it can have associated with some magnitude as well as phase. So this is arbitrariness. This helps us to say that actually the state space actually not the complete Hilbert space but the projective Hilbert space. That's why when we have the final wave functions, we say that we normalize it. Normalize means you are scaling down to such a vector which has norm 1, and but you may still have the phase ambiguity. You can fix the phase also. So then you uniquely identify one vector from the rays. So you can say these rays form some sort of equivalence class of vectors. Okay, the equivalence class also Professor Dashgupta has introduced for you. And the slide has become smaller, but reduced. Okay. I think there is problem with again internet. Maybe Annesha, if you are there, are you there?
Yes,
Annesha, if you are there, can you just
yes,
share?
sir. I'm sharing the screen.
Yeah. Yeah. Okay. Just go. Next slide. Slide 17. So, the slide before that. So, this, you can think of these rays are the basically represent your physical states, and you take any pair of elements from two such rays, psi and phi, you define their inner product in this way, and they satisfy the inner product should satisfy these conditions. Psi comma phi star complex conjugation will be phi psi. This first slot and second slot they get interchanged, and the linearity in the first argument. So naturally, from the first postulate, it will be antilinear in the second argument. Okay, and associated with this inner product, there is a norm which is always positive semi-definite, and will vanish only if the state itself, psi itself, vanishes. Now, observables are represented by Hermitian operators, which act on some states psi to give you some state psi prime, which is equal to a psi. And since they're Hermitian, they admit only real eigenvalues, so designate by alpha I. So a psi I equal to alpha I psi I. And if you have a pair of eigenvectors having distinct eigenvalues, then they are necessarily orthogonal. If the statement of psi I psi j is equal to 0 if alpha I is not equal to alpha j. Okay. Please go to the next slide. So here, what I'll do is that I'll take this A to be actually not a single observable, but all sets of commuting, maximum number of commuting observables. So a state will be exhaustively labeled by the eigenvalues of these operators. Okay. So collectively, I denote that by just A. So after measurement, immediately after measurement, the system belonging to a ray R state psi belonging to R will collapse to one of its eigenstates, Rn, with associated probabilities, which is obtained by taking the mod square of the inner product, psi comma psi n, and psi n belongs to the Rn. Rn is one such rays out of many rays to which it can possibly collapse after measurement. And the set psi n is assumed to provide a complete set of bases for the Hilbert space, so that if you sum over all such probabilities for all possible collapse state, then it should add up to identity 1. Further, the symmetry operation is defined by where this original ray is transferred to R prime, and the rays which are obtained post measurement, Rn's, that transform to corresponding with the primes, Rn primes. And symmetry operation by definition requires that probabilities are preserved. That means whether some observer assigns some ray to a state and some observer assigns some other rays R prime before measurement, and post measurement this pair of observables assign Rn and Rn prime to this set of states, then the probabilities of the collapse will be basically remain invariant. It will be preserved under the collapse procedure. Okay. Okay. Can you go to the next slide, please? Okay. Now let me come to a very important topic or theorem. This is called very celebrated Williams theorem. Obviously, I'm not going to give any proof for that. He says that this theorem says that to every such symmetry operator, means you can implement it only by a unitary or anti-unitary operator in the Hilbert space. Okay, so U is either linear in unitary. The unitarity is defined like this, and linearity is defined as xi and eta will come out unaffected, and u phi is u psi is equal to phi u. So the pair of vectors for which you are taking the inner product will remain unaffected, provided phi and psi are both subjected to the same unitary transformation u. Okay. For antilinearity, anti-unitary is almost same, except that you have to put another complex conjugation operation after you carry out this inner product calculation. And also it is anti-unitary. The xi and eta, for example, will come out as their complex conjugates, xi star and eta star, after the operation is over. Okay. Also note that adjoint of a linear operator is defined like this. In contrast, the corresponding adjoint of an anti-linear operator is defined as this thing. The difference is that only, again, you have to take a complex conjugation at the end. Okay. In either case, you can prove that u dagger u is equal to 1, and the subgroup SO2, which is connected to the identity, must be represented by unitary linear transformation. Since we are considering only the subgroup, which is proper orthogonal group L plus up arrow, that is, time is going in the forward direction itself. I am not considering time reversal. We are also not considering a space reversal transformation. So it is L plus up arrow, which is the part which is connected to the identity. And for this, it is necessarily implemented. Any transformation will be implemented through unitary transformation. It is mainly for time reversal symmetry that we encounter anti-linear operator. So we are not going to talk about it today. So this is a celebrated Wigner's theorem. You can see good books like, I'm basically following Steven Weinberg's book on quantum field theory, there is an elaborate discussion on these things. So Wigner's theorem also proof is there. If you are interested, you can go through it. That's the only source that I know which has discussed this in such a nice way. Okay. Okay, go to the next slide. Next. Now let me consider some projective representation very briefly, although I not use it, just mention because some of you may be surprised that if I am considering the vectors in the projective representation, that means there is an equivalence class. So I know the symmetry transformation will act on a specific state psi n belong to Rn, say. Okay, rather than Rn as a whole, it will not Rn. You have to take on some specific state. Now, if you carry out two such successive transformation, ut1, ut2, acting on psi n, it should provide a unitary representation ut2, t1, but you may ask the question that it may develop a phase, because upon arrival you don't know which means up to a phase you may arrive on the same ray. So phase is a bit undetermined, and particularly this phase may depend on which state psi n it is acting on. But it can be shown that it is independent of psi n. So this phase will depend upon these two operators, linear operators t1, t2, in the form of e to the power phi t2, tn. So it will be independent of which psi n it is acting. And if some non-trivial phi you can get is called a projective representation. And if phi is 0, we have a proper representation. Again, we restrict here to proper representation. Next, go to the next slide. I'm probably running out of time, but I have to accelerate a little bit. Okay. So
you have half an hour still.
Quite a more slides. It is difficult to estimate. I've never given this kind of online talk like this way, so it was a bit difficult. Anyway.
Please carry on it. Work. Yeah.
So consider now this ISO 1,3 transformation. I want to find the representation of this Poincare group, and again I told you the thumb rule is you have to find the generators, you have to find or consider elements close to the identity operation. So consider an infinitely small ISO 3 transformation. So first write x mu going to x prime is lambda mu mu x mu plus some translation epsilon mu. Epsilon mu I can immediately take it to be very small. For lambda mu nu, I have to write it delta mu nu plus omega mu nu. Okay, you can see that whenever I write this kind of transformation is involving Lorentz transformation, I have to deliberately write like this lambda mu top and slightly shifted in the right to the bottom index subscript mu. This is to make room for the row and column indices. Otherwise, there will be ambiguity, which is row index, which is column index. Okay, and so again, when means it will become clear when in the next line itself that omega mu nu's are infinitely small, and both omega like epsilon mu, so their magnitudes are very very small than 1, and omega mu nu means if I the way I have written, if I lower it using eta, the row will come down as mu in the as a subscript. Only after I bring it down, it will become completely covariant second-rank tensor, antisymmetric tensor, and it will be antisymmetric. That you can easily prove by just substituting it here and retaining only the first order term. So again, you see this omega mu nu represents the generator of the Lorentz transformation in the mu nu plane. So if it involves one is 0 component, omega 0 I will be the boost parameter, and omega ij's are the rotation in the ijth plane. So again, there are 6 of them, okay, 4C2, 6 of independent components, which is the same as the number of SL2C parameters of generators, okay. So again, it will split into 3 boost and 3 rotation generators. So in the vicinity of the identity is these things, U1, 0 is just denoted by 1. So you can write down this as some combination of the Lie algebra generators, which where P0 is identified with the Hamiltonian. Okay, let's go to the next slide. Again, just before going to the next slide, I just want to mention again J mu will be antisymmetric and they are Hermitian, and omega mu nu also will be antisymmetric as I told you. So there will be double counting. That's why I had to put a prefactor half in front of it. Okay, so J mu is antisymmetric, it will be Hermitian, and like P mu also. Now make use of this identity. Now you consider this the product U lambda A, U identity plus omega comma epsilon, U inverse lambda A, and if you just take the make use of the product rule I have given you up to the first order, you will get this kind of term. U identity plus lambda omega lambda inverse, and another term will get lambda epsilon minus lambda omega lambda inverse acting on A. Now all that you have to do, you just identify the coefficients of omega mu nu epsilon mu, and you will end up with this kind of relations which is enclosed in 2 boxes. And while identifying extracting the coefficients of omega mu nu and epsilon mu, particularly for omega mu nu, you should be very careful because they are antisymmetric. So the factor sitting in front of it also should be antisymmetrized. Otherwise, we'll end up into some wrong expression. Okay, you should be careful about that. And once you do that, you will find that it will satisfy this kind of relation. The first term on the right hand side shows that it transforms like a Lorentz tensor, except that you get further, almost transforms like a Lorentz tensor, but in presence of translation, it will fail to transform like a Lorentz tensor. But if the A mu's are 0, it will transform like a second rank antisymmetric tensor. Okay, and P mu will transform like a 4 vector. It is not affected by translation. After all, it is the generated translations. And this is not surprising because angular momentum operator in depends upon the origin you are choosing to define. Okay, it's sensitive to the choice of origin. Okay. So next, go to the next slide. Next slide, Annesha, next slide. Darsha, can you hear me? Next slide, please. Huh. As I told you, under homogeneous Lorentz transformation, GMU transform is a tensor, PMU is a vector. Oh. Now it has disappeared. Annesha's got disconnected. So again, Atri, I had to request you.
Yeah, I'm just doing it. Just I could see that she got disconnected. Just loading. I have to get to the right page just. Is that okay? I'm just going down. Can anyone tell me what the page number?
The page number is, yeah, no, go to the next page. Go to the next page. Right.
This is the correct
Yeah,
one,
yeah,
right?
yeah, yeah.
Yeah, I just wanted 22.
Okay. So now, special cases, homogeneous Lorentz transformation translation is equal to 0. You find that JMU transforms like a second rank tensor, antisymmetric tensor, and PMU is a 4 vector. Under pure translation, JMU again doesn't transform like a tensor, it gets the additive part. Now, here you see the way I have determined it, I have used the infinitesimal version to derive this transformation property. But now, towards the, if I want to go towards the derivation of the Poincare algebra itself, we again substitute the infinitesimal version of this u lambda a in the form of u IDQ plus omega epsilon, which I used already earlier in these above relations. And then everything means you see that Lorentz generator, Poincare generators, J mu and P mu will be sandwiched between these infinitesimal u IDT plus omega comma epsilon. And again, you have to do what you have to do. You have to identify the coefficients of omega mu epsilon mu. And this way, you can see since there's an adjoint action in the infinitesimal level, they will give you commutator, and you end up with the commutation relations of the Lie algebra of ISO 1,3, which is given in the next slide. Next slide, please. Okay, so now let me discuss what are the conserved quantities and Casimir operators. So for that, it will be easier to split this four-dimensional covariant form of the Poincare algebra into 1 plus 3-dimensional notation, usually 3 vectors and things like that. So just denote J23 as J1, J31 as J2, J12 as J3, the cyclic manner. Okay. So call it just J. So you can see that the Lorentz generators are Ji, Jj is equal to I epsilon Jk, Jk. This is expected. You will get the SO3 algebra. Ji, Kj will give you I epsilon Ijk, Kk. It shows that K is transformed under rotation, usual SO3 rotation. And Ki, Kj gives you minus I epsilon Ijk, Jk. It shows that boosts do not form a subalgebra. It doesn't close, in other words. Okay. And Gi, Pj will give you I epsilon Ijk, Pk. And Ki, Pj will give you IH delta Ij. Both P and Ks are 3 vectors under SO3. Go to the next slide. And from this algebra, GIH commutator, PIH commutator 0 shows that P and J's are conserved. But P0 is by itself H. Okay? And KIH is mine IPI, the boosts are not conserved. And so these comes from what are the conserved quantities that will come obtained from the Lie algebra sector. But as for angular momentum, you recall that only J3 you can take it to one of the commuting observables from J1, J2, J3, but additional conserved quantities are furnished by the Casimir operator. So you can here also ask, are there any Casimir operators? The answer is the affirmative. There are two such Casimir operators. One is P mu, another is W mu, W mu. The W mu is defined like this: I epsilon mu lambda rho is J mu lambda P sigma sigma, and this is called Pauli-Levinsky vector, and it is designed in such a way that it extracts the spin component of the angular momentum that any particle may have. Because if you see J nu lambda, if it is of the form as I discussed yesterday, in general, if you consider multi-component wave functions, then you not only have the orbital angular momentum part, but also the spin part. Spin part cannot be obtained from structures like R cross P. It is only the orbital angular momentum which can be obtained by this. So J nu lambda, you can write it as the L nu lambda plus S nu lambda. S nu is the spin part, which is not of the form of R cross P, but L contains the P. So L part, since you will have another P nu, P lambda, one of these terms occurring there in the orbital part, and P sigma is already there on the outside. So you will have two indices under which it will be symmetric, and it's being contracted by epsilon tensor where it is antisymmetric. So it will automatically cancel, and you are left with only the speed part. So if you can go further to the rest frame of the particle, then it will get basically the J square term. As you can easily check, W mu will be minus M square J square psi. So usual, if you go to the rest frame, you will get S into S plus 1 as the spin of the particle, which will be restricted to half, 1, 3 by 2, and things like that, corresponding to different SU2 representations. And the M square comes from the Casimir eigenvalue of the P mu operator, which is minus M square. Okay, so these are the two. So what is the nice thing is that all the particles, elementary particles, standard space-time symmetries tell you that all the particles can be classified according to these two Casimir operators, and these two Casimir operators, mass and speed. So this classification is very important. So all the particles, so apart from that, there are other conserved quantities, means you will see in the particle physics they talk about all other, even electric charge and all these things, but it is not coming from your space-time symmetries. So space-time symmetries tell you these are the quantum numbers, and different particles, they transform according to the different representation of the same underlying Poincare grid. So the representation will be dictated by this mass and speed quantum number. Okay. Please go to the next slide.
Professor, can you ask a question?
Oh, last. Okay. So yeah. Oh, it is the last. Okay. So tomorrow I will talk about the Wagner little group. I particularly focus my attention to one particle sector and Wagner little group, and particularly I try to show you how helicity can be defined for the massless particle and all that. It's a very nice thing to know about the Wagner. It was a beautiful construct. Okay, so if you have any further questions, please ask me. Just related to that.
Yeah. Please, Sumit is speaking.
Professor, can I ask a question? Yes, I'm Shumit.
Yes.
Yeah. Why? How can we be sure that there are only two Casimir operators? I mean, are there any Casimir operators, possible Casimir operators, or is there any relation between number of Casimir operators or something in the group itself?
Yeah, generally compact Lie groups, there is a miss. For example, this rank of the, you have already seen the Cartan sub-algebra and all these things, okay?
Okay, it's equal to the rank of the
rank of the Cartan sub-algebra, something like this. So, but here it is a non-compact group. So
yes.
that you cannot apply, I think, directly. But it is well studied, and it is known that in this case also means you can, for example, one subgroup is the SO3 group. From there you can get the W mu is basically the generalization of that. As I explained just now, you can go to the rest frame of the massive particle, and it gives you the J square eigenvalue basically, the last equation you can see. And the P mu is the massive. This is the only thing you can think of. There is nothing else. Means P mu is a generator of translation, and from Einstein's energy momentum relation, P mu gives you mass square, right?
Yes.
So it has to be satisfied. An angular momentum, and as I told you, the boost is not a conserved quantity. So the only three angular momentums should come into play. The thing is that in the J square case, we have identified going to the rest frame. You can cast going in the opposite direction in the form of Pauli-Lubansky vector in four vector and pseudo vector actually it is. And but W mu is a scalar, so it will be invariant under Lorentz transformation. And going to the rest frame is you don't lose any generality.
Yes, I can just boost it.
Yeah, you can boost it, but W will not be affected.
Will not change. It will remain
Yeah.
invariant.
Yeah.
Okay. And Professor, another thing you mentioned that to represent non-compact group in unitary representation, it should be or it necessarily be infinite dimensional. How can you say that? I mean, it's not clear to me that why should it be infinite dimensional?
Well, frankly speaking, I also don't know the correct answer. I don't know. This is a mathematical theorem that I can tell you. I don't know whether Sachin has a better answer to it. This is a well-known theorem. Means I cannot prove it a priori, but we know it is a matter of fact. Okay. I don't know. Sachin probably has left. Probably could have said something better.
Okay, Professor.
Yes.
Hello, sir.
Yeah.
Hello.
Yes, sir.
Yeah.
Sir, as we know that time reversal symmetry is an anti-unitary symmetry.
Yeah.
So,
I have
sir,
not
sir,
discussed.
I just want to know, sir, is there any example of other example of anti-unitary symmetry? Can you give?
Yeah, charge conjugation, as I told you, charge conjugation operator is an anti-unitary.
Sir, if the boosts are not conserved, so that means there is a changing in energy.
Yeah, if you keep on boosting, then you have to supply energy. No, how the particle is going to accelerate. Means if you take a particle and if it goes on accelerating, you have to supply energy to the system. So it is obviously not conserved.
Okay, sir.
Sir, I have one question.
Yes.
Yes, sir. I was asking if the Dirac equation, is it a consequence of SL2, C symmetry itself?
Yeah, means you can find. You see, when you write learn tensor analysis, you learn scalar and vector and things like that. But in between, you also have interpolating the spinors. And the moment you find that this SL2C, as I told you, is a double cover. SL2C by Z2 is SO1, 3, right? So it provides a double cover. So you find there are objects like the spinors, SL2C spinors, which also transform non-trivially under Lorentz transformation. And all that you have to do is that those are transforming according to the left representation and the right representation. You have to just put them together to form a 4-component Dirac spinors, so that it provides an irreducible under the enlarged Lorentz group, which includes the parity symmetry or space reversal symmetry also. And then you find that it has to transform in this way. So it is from simple kinematical consideration you will end up with this thing. It is of the same stature as p square plus m square equal to 0. That kind of statement. You can, in fact, you can think of it as like this way. Means just like you consider suppose a 2-dimensional Laplacian operator, del 1 square plus del 2 square. You can ask the question: is there any operator which can be regarded as square root of this thing? The answer is yes. You just write sigma 1 del x plus sigma 2 del y. Okay, you take the square, you will find that it will give you the Laplacian in 2 dimensions. So Dirac operator is just that, the square root of the Laplacian operator. And so you take the Klein-Gordon equation and somehow you take the square root but there you involve another means four such terms, and there is a negative sign also. Lorentzian signature is involved there, but nonetheless, the essentially the same idea is involved. If you take the square root of it, you get the basically Dirac operator gamma mu p mu plus m, something like this. That's why all the components individually satisfy the Klein-Gordon equation, which it must, because Klein-Gordon equation is a consequence of the Einstein's energy momentum relation. It's p squared plus m squared equal to 0 in our signature convention. Okay. Any other question?
Sir, can you hear me?
Yeah, tell me.
Oh, sir, so for the Dirac spinors, as you were telling that you are considering them to be classical, but then you are also assigning like this spin half to them. So, and we know that this spin is completely
yeah. But here I am saying that here, of course, my means if I strictly means it is something I imported some quantum knowledge from field theory, say. But here, all that I can say that the eigenvalue of sigma dot p hat on psi r is plus 1 or minus 1. I don't know a priori that it will be related to the spin or something like that. Okay, up to this I can say. But now what happens is that, as I'll show you tomorrow, this is the component of angular momentum in the direction of momentum is called helicity operator. There are reasons that this helicity operator has to be the only thing which survives the description of the angular momentum content of a relativistic massless particle. Okay. Now, and it is also Lorentz invariant concept. The thing is that one cannot argue from simple group theoretical argument that this object, the eigenvalue, has to be restricted to 0, half, 1 or something like this. For this, one has to invoke some topological argument, which I am not. I don't have time to discuss. But if you are interested, again, you can see Weinberg's book of quantum field theory, which has discussed quite extensively topological argument, which shows that it has to be restricted to those values. So I've just have told you those results in advance, but otherwise all the discussions were essentially classical.
Yes, so sir, for even for classical case, if we just consider them like the components as Grassmann variables, so won't that also take into account that they can be considered as spin half particles?
I couldn't follow your question. You tell me again.
I am saying that even if we consider the direct spinors as the classical, but then also that the components are as Grassmann variables. So won't that also
components are
Grassmann variables that is used to for the Dirac spinors?
Grassmann, that comes again from the classical. You go to quantum, again come back to the classical level. Then you find the classical description will be classical. This is another story altogether. But you see here, I have not made use of any Grassmann nature. I did not have to make use of any Grassmann nature. As I have some two-component objects, which values in C2. Here I have taken to be some complex number, but you could have multiplied them some Grassmann number to form a Grassmann algebra. Because nowhere I have made use of their non-Grassmannity in nature, so that my analysis will fail somewhere. Okay, it will go through.
So it's mostly like a more like a mathematical construct, like everything is following from the group theory. So physical implications are not very much apparent.
No. Physical application. I have not intended to study the physics part of it here. Physics part will come when you do quantum field theory and things like that. Again, in between, you will try quantum mechanics, relativistic quantum mechanics. Then you will find that it is incomplete. Then you have to go to quantum field theory. Historically, if you try to develop it like this. But if you read Weinberg's book, you will realize that how nicely he has gone through this kind of analysis, Weinberg's little group, And Windgren's little group tells you, although it is a subgroup that I will define tomorrow, the transformation property under Windgren's little group dictates how the transformation property under bigger Lorentz group would be like. Okay. So using this, he wanted to construct the quantum field theory, and he shows in his book that why quantum field theory becomes quite indispensable if you want to have a successful merger of special relativity with quantum mechanics. Okay.
Okay. Thank you.
Anything else?
Hello.
Okay then. Hello. How is? Any other question? Any you have? Okay. If there are no further question, let us pause for a while and wait till Frederick's talk starts within half an hour's time. Okay. Okay. Is it?
Hello. You have a lecture tomorrow.
Yeah.
So if there is any question,
Yeah.
you take those questions just before the next class.
Yeah.
So we stop here for
Yeah. You see, my lectures are very elementary compared to the other lectures that you are going to attend